Hi, we're working on a new unit today. Unequal heating, insolation, albedo. We're actually talking about wind. So the entire Earth is heated by solar energy. It's where all of our energy comes from. The tropics are heated more than the poles. There's an imbalance in that heating, and it's redistributed. Solar heating and movement of heat by oceans and the atmosphere determines the distribution of our temperature, precipitation, ice, even the vegetation. So, for a new vocabulary word, insolation. Insolation is incoming solar radiation, or the amount of solar radiation that's received at the Earth's surface. The sun emits all wavelengths of the electromagnetic spectrum. It's called solar radiation. About 50% of the solar radiation that comes into the Earth's surface is in the visible light portion of the EM spectrum, which is right in this area. And that is what we use to heat our Earth. So there's 6 factors that you need to know about that affect insolation. So the angle of insolation. The intensity of insolation increases as the insolation gets closer to 90 degrees. You can see here as the sun comes down at 90 degrees, it's very concentrated into one area. The intensity of insolation decreases with increasing latitude. And the angle of insolation varies throughout the day. When we have a 45-degree angle, look how much more the energy is spread out. Okay, the duration of insolation, the length of time that the Earth's surface receives insolation. The surface temperature at a particular location on Earth is directly related to the duration, the time of insolation. The duration of insolation varies with latitude and the season of the year. So maximum insolation occurs in the northern hemisphere around June 21st, which is the summer solstice. Maximum surface temperature occurs on Earth's surface after the maximum duration of insolation. So here in June, around the 21st, we have the longest day, which means that we have the most sunlight hitting the Earth. And the average annual surface temperature on Earth is inversely related to the latitude location. So as we move up in latitude, we get up into Alaska and the Arctic Circle. Even if the day is long, it's going to be a lower surface temperature. Okay. Absorption and reflection of insolation. About 19% of incoming solar radiation is absorbed into the atmosphere. So we start out with only 19%. Of that, 47% is absorbed by the Earth's surface. So reflecting, about 34% of insolation received by the Earth is reflected into space by the clouds immediately, by snow caps, ice caps, and water. Scattering of insolation. Insolation can be scattered by the molecules of gas, water, or dust in the Earth's atmosphere. This is actually why the sky is blue. And last is energy conversion. Insolation can be transferred into stored potential energy, latent heat, by evaporation of water or sublimation of ice. So all of these are what helps to make our climate the way that it is. The Earth's climate itself is very temperate. It allows us to live there, and we need all of these working in tandem in order to keep it that way. If the Earth was flat with no atmosphere, solar radiation would be too intense for any life. Because the Earth is round and rotating, the solar energy is cut down by 1/4, making it possible for an atmosphere and for life on Earth. This is all mathematical. You don't need to know the math, but you do need to know that this hemisphere, this hemispheric rotation, allows us to have a very temperate Earth. And as we said before, that about 30% of the energy is reflected by clouds, dust, and the surface. Okay, Earth's temperature is constant. It's somewhere around 15 degrees Celsius. Energy loss has to equal incoming energy. Okay, so it has to budget together. Earth is constantly receiving heat from the sun, so there has to be an equal amount of loss of heat back to space. So, if Earth's average temperature is actually about 15 degrees Celsius, there would be an assumption that the surface of Earth would also radiate 15 degrees Celsius. So, the amount of energy coming in is 15 degrees, the amount going out should be 15 degrees. However, satellite data doesn't say that. It says that the Earth is only radiating an average temperature of negative 16 degrees Celsius. So, why is there a discrepancy? What accounts for the 31 degrees Celsius difference? That's an enormous amount. Enormous amount. So it's greenhouse gases. They absorb 95% of the long wave radiation emitted from the Earth's surface. It's trapped radiation re-radiated back down to the Earth's surface, and it accounts for the 31 degrees Celsius heating. Satellites don't detect radiation. There's a muffled effect from the greenhouse gases, but this is what keeps Earth's temperature in balance. So the greenhouse effect isn't bad. It's actually the way in which heat is trapped close to the surface of the Earth by greenhouse gases. These heat treating stop. The greenhouse effect is not really bad. It's the actual way in which heat is trapped close to the surface of the Earth by the greenhouse gases. The heat trapping gases can be thought of like a blanket that wraps around the Earth, which keeps it toasty, and it wouldn't be warm without it. Greenhouse gases include carbon dioxide, methane, nitrous oxides. They arise naturally, and they're part of the makeup of our atmosphere. Earth is sometimes called the Goldilocks planet. It's not too hot, it's not too cold. The conditions are just right for life, including us. Part of what makes Earth so great for life is the naturally arising greenhouse effect, which keeps the planet a friendly 15 degrees Celsius, about 59 degrees Fahrenheit on average. But in the last century or so, humans have been interfering with the energy balance of the planet, mainly through the burning of fossil fuels that give off additional carbon dioxide into the air. The level of carbon dioxide in the Earth's atmosphere has been rising constantly for decades and traps extra heat near the surface of the Earth, causing temperatures to rise. So these are the greenhouse gases that you need to know: water vapor, carbon dioxide, methane, nitrous oxide. And then the clouds also trap some of this. Okay. Variations in heat balances. Some of it's because of incoming solar radiation. It's stronger at low latitudes, 0, the equator. It's weaker at high latitudes, up in the Arctic poles, either north or south. The tropics receive more solar radiation per unit than the poles. Some of that has to do with the distance to the sun and with the angle that the sun comes in. So what else affects the variation in heat balance? Well, solar radiation arrives at a low angle. Snow and ice reflect more radiation at high latitudes. It's called albedo, percentage of incoming solar radiation that's reflected rather than absorbed. So you see here in the picture that ice, white, reflects a huge amount of light, where black, the land, will absorb a huge amount of light. It's one of the reasons why we wear white in the summer and dark colors in the winter. Have you ever seen how bright the sun is when it's reflected off of snow? That would be because snow has a high albedo. Albedo is a measure of how much light is reflected back from a body. It usually refers to planetary bodies, like Earth, and the amount of sunlight that's reflected back into space. Earth's average albedo is 0.3 to 0.35, which means 30% to 35% of the sunlight is reflected back into space. What happens when the sunlight is not reflected? The other 65 to 70% of the sunlight gets absorbed by the earth. Dark ocean water, trees, and dark soil absorb a lot of the sun's energy, and that's what keeps us warm. Imagine the difference between leaving a bicycle with a black seat or a white seat in the sun. The black seat will absorb more energy from the sun, which would make you feel the heat. For Earth, a lower albedo would mean that Earth reflects less energy, so the Earth would be a warmer temperature. Obviously, then, higher albedo would create a cooling effect. Different surfaces on Earth have different albedos and different effects. The polar ice caps have a higher albedo, so they reflect more sunlight, creating a cooler environment. Rainforests have a low albedo, therefore they have a warmer climate. All of Earth's surfaces absorb more solar radiation from an overhead sun. Water reflects less than 5% radiation from the overhead sun. Water does reflect high fraction of radiation from a low-lying sun. Earth's average albedo is about 10%. But look at the difference between high, about 5% is reflected, low sun, about 33% is reflected. Incoming solar radiation per unit is higher in the tropics than in the poles. The sun angle is higher in the poles than the tropics. Albedo is higher at the poles than the tropics, and variation in cloud cover affects the heat imbalance. So if you see, reflected by the Earth's surface, snow. The tilt of the Earth's axis results in seasonal change in solar radiation in each hemisphere. About 50 million square kilometers of the Earth's terrestrial surface undergoes a transition each year from freeze to thaw, thus setting off a series of processes in the global biosphere. Much of this activity can be detected by the changes over time in the amount of sunlight that's reflected from the Earth's surface at various wavelengths. A quantitative measurement of this reflected sunlight is described by the albedo, which is the fraction of sunlight reflected from a surface area. The surface albedo can vary between 0, all light is absorbed, and none. Fresh snow is an example of a surface type with an albedo close to 1 in the visible light and solar spectrum, whereas the deep, clean ocean water has an albedo close to 0. Notice that the x-axis represents months of the years and the y-axis is the latitude. The coloration of this graph represents solar radiation. The darker the color, the greater the solar radiation. If we were to draw a horizontal line across the equator, you can see that the seasonal change in solar radiation is not that great. However, if a line is drawn at 40 degrees north or south, you can see that the radiation levels differ greatly throughout the year. Increases in northern hemisphere winter albedo, due mainly to snow cover and to a lesser degree the Arctic sea ice, increases southern hemisphere winter albedo during sea ice. Stop. Increases in northern hemisphere winter albedo, due mainly to snow cover and to a lesser degree the Arctic sea ice. It increases the southern hemisphere's winter albedo due to sea ice. Stop. There are seasonal albedo changes in the Arctic and the Antarctic due to sea ice and snow. The ice albedo feedback is an example of a positive feedback loop. A feedback loop is a cycle within a system that increases positively or decreases negatively the effects on that system. In the Arctic, melting ice exposes more dark ocean, lower albedo, which in turn absorbs more heat and causes more ice to melt. And the cycle continues. When you heat up a pot of water on the stove, which one heats up first, the pot or the water? Well, the pot heats up faster, although you're putting the same amount of heat into both substances. The pot responds quicker than the water because water has high heat capacity. Heat capacity, remember, is the measure of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. In this example, water has a very high heat capacity, which means it requires a lot of heat or energy to change its temperature. Additionally, to temperature, it takes a tremendous amount of energy to change the water molecules from one state to another. On Earth, we have 3 states of water: solid, liquid, and gas. And they're actually resistant between going back and forth from one another because water has a high specific heat. That's why through the course of a warm summer day, the water in the ocean does not experience a significant change. Land, on the other hand, has a much lower heat capacity. For these reasons, the ocean takes a long time to change temperature significantly, whereas land can heat up very quickly. Think of the hot sand and the cool water at the beach during the summer. Since air travels around, air temperature is also regulated by these principles. Air that is in contact with the ocean will be much cooler from the energy transfer between the water and the air, while air that sits above the land will heat up much more quickly. Therefore, coastal climates are much more temperate because a body of water is nearby to regulate the temperature and keep it more constant. On hot days of summer, landlocked places such as the Midwestern United States are much warmer than coastal cities at the same latitude because the land gets heated up quickly and can't disperse the heat.